So, I hope you said nice things in your survey. Alright, so you've got the page there. Let's have a look at number 5. So you have Young's double slit, and here has a narrow parallel slit cut through it of width 0.5 placed 9.5. In Young's double slit experiment, a beam of laser light falls perpendicularly onto a metal plate which has two narrow parallel slits cut through it. Okay, so I better draw this a bit better. So you have your plate, and you have one slit, then you have another slit, and these are 0.15 millimeters. And then you're told that they are 0.9 millimeters apart. And then there's a screen, and the distance here is 1.1. And you know the story. What do you get on the screen here? Yeah? The fringes, yeah. So you get like one here, and here, and here, and here, and here, and here's n equals 0. The distance from the middle of the central fringe to the middle of the 10th flight fringe is 5.5 millimeters. So, okay, let's pretend I did 10 of these, okay? I know there's not 10 here. So here is n equals 10. Dot, 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 dot. And they give me the distance between these. They say the distance is, what is it? 5.5 millimeters. So if the distance there between the 10 is 5.5 to the 10th dot, then how far apart between each dot? Well, that would be 0.55 millimeters. Well, anyway, the first question is in the calculation. It says, what is meant by diffraction? Okay, so what does diffraction mean? What's diffraction? Does anyone know that one? Yeah? Yeah. So diffraction is the spreading out of a wave as it passes through a slit. B. What is meant by interference? So what's interference? Who? What's interference?
When two waves come together, they form new wave, which is
etc., etc., etc. Yes, you're right. So interference is the combining of two or more waves to make a new wave, etc., etc., etc. Right, part C is they want the they want the wavelength. So we can use the formula lambda equals d over df. Is that the formula?
Big D over here. No, big D over
S equals big D.
Yeah, so if I rewrite it, it's like this. Yeah? No? Oh, this is for S, is it? I gave you the formula. What is it? Read it out to me. S equals big D over small d lambda. So therefore, lambda equals small d over big D S. Yeah. So then lambda equals, okay, so we need to put in our numbers. The big D is 1.1. And the S is, this is the S here, 0.55. Yeah. Now the question though is, what is the small d? So if I go back here, can I go up? Yeah. So the question is this the small d or is this? I think so, but I'm not 100% confident. Let me have a quick check here. Can you read out the formula? What was it? S equals big D over small d times lambda. Yeah. Was that the formula?
Yeah.
I have it the right way around?
Yeah.
Okay. Looking like the D is the gap between the slits, not the gap of the slits. You disagree or agree, who?
Not very clear.
It's not very clear. I think.
I just think I know the D is the gap between the slits.
It is the gap between the slits.
Serious? I found that out just because of they gave an answer, so you just work backwards.
Oh wait, we have the answer right here, so we know if we got it right or wrong. But if I look here, here's our formula we're using. You can see it there? And the D is the gap between the slits. So we can continue. What number was it?
0.9.
So 0.9 millimeters, huh? 0.9 times 10 to the minus 3.
It's 4.7 times 10 to the 4.5.
It does come out correctly as 450 nanometers. Great. And finally, 450 nanometers. What color of light is that? Well, is it that big? If we remember, I think visible light is 550 nanometers. So around about this. I don't know, Ugo, if it would be X-rays. I don't think it's that small. Do you remember here? This is small lambda, big lambda, and then here would be like X-rays, and then here is like radio. So this one here is 550 times 10 to the minus 9. So this is around about 10 to the minus 6. Here, let's have a look at our electromagnetic spectrum graph. I feel like if it's 450, that's a little bit smaller. I don't know, I think it might be like violet, maybe ultraviolet. I don't know. Let's have a look. Oh, come on. Here we go. 10 to the minus 6 is, well, I don't quite have 10 to the minus 6. I have around about 10 to the minus 6. That is infrared. It's 10 to the minus 6, isn't it? Well, I mean, it's just a kind of a threshold. Visible light is, there, look, nanometers. Yeah, visible light is 400 to 700 nanometers. So in the middle is around about 550 is the middle. So if we have 450, that would be, yeah, ultraviolet or violet. 450, violet. So the light would be a purple colour. Yeah. This is how I remember it. I remember that 550 is the middle. So here 450 is around about, here. Okay? And do you remember the colours? It goes red, orange, yellow, green, blue, indigo, violet. And then after this is ultraviolet, all the way up until X-ray. And then around about here at radio, that would be around about, I don't know, 10 to the 2, 10 to the 3. Okay. So a purpley colour is the answer for part D. A purple colour light. Something like this. Okay. Is that okay for you? You had trouble with this? So what did you ask me to do it?
No, because you draw the picture, so I can't get it.
The picture was all you needed, yeah? So you could have told me to stop then. And that's okay, I'm just joking. You have this drawn, you have this done, written down? Yeah, it's okay then? So we'll have a look now at the last topic. Okay. Let me get you a video. I hate these. Give me an actual moving one. Here, this guy. There we go. So this is that's just a string, okay? In white is a string, and here is a little motor, a little engine, and you can see he's just explaining that the engine will move the string. So you can see it going up and down, and then you make it go faster. See what's happening? So you kind of have this wave, but it's a little bit strange because the wave's not moving anywhere. It's not like a sound wave. Oh, come on. Yeah, he's explaining. So, It's moving up and down, but look at the very middle. There is the slow motion. You see in the middle, it's not moving. It's like, oh, it's gone. Here. You see here, right here, it's not moving, but it's moving the most here. This is called a standing wave or a stationary wave. Okay, I think that's enough of him, unless he has something more interesting to show. Yeah, look. Okay, thank you. So let's have a look now at this. This is called looking at standing waves. So we have this wave coming in, and when a wave hits the surface here, it will bounce back. Like my sound wave, you all know what an echo is? You know echo? Do you know echo? Echo is when you say something and then you hear it again. Like when you're in a cave, or you're in a building. If you say something and then you say...
In a queue?
Where?
In a queue.
What do you mean?
Hill.
Hill? Yeah, like a hill in the valley. So you say something really loud, and then you hear it again. Yeah, it comes back, yeah. This is called an echo. And this is because I think what you're picturing, Louise, is if you're standing on a hill on top of a valley, maybe something like this. So you say something really loud, and then you hear it back later. This is because the wave hits the wall and then comes back. This is called, the verb here is reflect. So it's reflection of waves. This is the wave coming back to you. A standing wave is a very special situation of a reflection. With a standing wave, what happens is the wave goes out, hits the wall, comes back, but the wave that comes back, it is, it's easier if I draw it first. So what you have here is, you have a wave like this, but then when the wave bounces off the wall and comes back, it comes back exactly out of phase with the original wave. So the wave comes in, you can imagine it's moving in like this, maybe whatever, sound wave, hits the wall. Now if you look here, wave goes up, down, up. And when it's back at the middle, what does it do? It goes up, down, up. So what does the wave want to do next? It wants to go up or down here. Does it want to go up or down? It wants to go up like this. But can it? No, instead it hits the wall and goes backwards. But it still wants to go up. So it ends up going up, down, and like this. So this is why it looks like the shape is like lots of O's. If you remember, if there's not the video up here, comes to maths. Yeah, don't ruin the surprise. No. Oh no, this is the next video. Yeah, I forget this. Right. Well, you saw this in the video with the string. These places here is where the wave does not move. These are called the nodes. Yeah, and then the other point where it moves the most, you get the name, you go for it? Antinodes. Now, you notice that this does not work in this situation. Can you look here? So imagine the wave goes up, down, a little bit up. This doesn't work here. What you need is the wave to fit into the distance. So we need the wavelength multiply some number to equal the distance, if I call the distance here L. In other words, you must have like 1, 2, 3 wavelengths. You can't have 1, 2, 3 and a little bit. It needs to fit perfectly inside the distance. No leftover space. Yeah. Okay. So let me go down. I can go down. So here is the wave, and here it fits once. Here is a wave, and here it fits once, twice. Then here is a wave, and then it fits once, twice, 3 times. So can you see here, this is 1 wavelength, this is 2 wavelengths, and here this one is 3 wavelengths. These situations have names. This is called the fundamental. This one is called the first harmonic, and then this one's called the second harmonic. Okay, let me just see if I can get a picture of that too for you. First harmonic wave. Sorry, I think I told you a lie. First harmonic, second harmonic. No, it's okay. That's what I have. Fundamental, yeah. First harmonic, second harmonic. Yeah, all good. Okay, so why do we care about these? Well, they have 2 interesting applications. Can I scroll down? Yep. Okay. So let me draw something here. Here is a pipe, like a cup, yeah. And there's a sound wave. We're putting some sound in the cup. Yes, are you understand? You okay here? Yeah. So you maybe, I think I drew this before for you, a tuning fork, did I?
Yes.
For the music, yeah. So you hit the fork against it to make some sound inside of it. So I'll draw, let me see, a couple of situations. So here's the first one. The wave is fundamental. Then here, the wave, let's say, is half of the wave is inside of it. Then here, there's a quarter of the wave inside of it. Yeah. So the pipe will shake. You know, if you put sound is a wave, so, you know, it will shake. Do you ever see something beside a loudspeaker shake? Okay, so it will shake. So my question is, which one will cause the pipe to shake the most? Which one will make it shake the most? First, second, or third? So you're going with first one? First one? Who?
I go with third one.
Third one? Ugo? First one? Sorry to tell you, unfortunately, who is right. It is the third one. Yeah. Now why, though, who? So you just guessed, yeah?
Because high.
Well, what happens is, this wave is going up and down, yeah? So the wave is going up here, and then here it's going down. So if there's a force going up, and there's a force going down, they kind of cancel. So it doesn't really move, right? What about here? There's a force going up. So this moves a bit, right? But why does this one move the most? Because there's a force going up as well. It's the same as the second one, but this one will move, vibrate more. Why is that, do you think? Any ideas? What's so different about these two that make this one the winner? Same, no, not the wavelength, no. Well, I'll tell you. If you calculate here, the turning force is the distance multiplied f. But here, the distance is bigger, isn't it? So what will happen is this will turn more than this one. So you get more of a shake. Yeah. So anyway, this one here vibrates. So let me call the distance here d. Who can tell me what the wavelength is if I know that this distance here is d? How many d's is it? 4. Because if you finish drawing the wave, it goes like this. Then it goes down, doesn't it? Then it goes down and back up. So you have 1, 2, 3, 4. So this is the first formula for today. This one here is vibrating pipe due to sound. Well, I suppose it doesn't have to be sound. Not in the formula book. Not in the formula book. Yeah. Let me give you one to try, okay? So here we have our pipe, and the pipe is 1.25 meters long, and the pipe is vibrating, shaking, because there's a sound going into it, a sound wave. And the sound wave has a speed of 340 meters per second. So my question is, what is the frequency? So you need to use the formula from last week as well, okay? So I'll give you a minute to try this. Okay, we got an answer? Answer, Louise? Or do you have an answer? No, not yet. Abraham? Yeah. Who?
Yes, but with some calculation.
Okay, so not yet. And Ugo? Tell me, have you seen Saeed in other classes? So you saw him what, one day in chemistry and that's been it?
Yes.
Okay, because I was just wondering if he's gone to chemistry but not maths and physics. So you saw him chemistry once and then that's it. Yeah. Okay, let's have a look at this. So the first thing I'll do is I know that the wavelength is 4 times 1.25. That's equal to 5 meters. What? Yes? And then we also know that V equals lambda F. So F equals V over lambda, which is 340 over 5, which is 64? 8. 68. 68. Okay, let me give you another one like this to try, and then we'll look at a different type. Sorry, can I go down? Yeah. So here is our pipe, and it's 0.85 meters long. And I want you to, number 1, draw the sound wave, and then number 2, show where the nodes and antinodes. Draw the second harmonic down. So you need to do this on another graph. So this is something on a separate graph. And then the last part we'll see if V equals 340, then what's the F? Okay, so it's a lot like the last one. So I'll just give you a minute to try that. Okay, got that finished? Not yet? Okay. You have the first part finished, Louise, don't you? Draw the sound wave?
Yeah, I finished the
Okay. So the first one, look up.
Yeah.
The sound wave is like this. Sorry, like this. Yeah. Now, where is the node? Which is this a node or an antinode?
How can I know the draw?
Well, I suppose because in the question it says it vibrates. Which I didn't actually tell you, sorry. I'm actually doing number 2 here on your page. It says it vibrates. So if the pipe vibrates, it's because the wave is like this. If I go back here, Louise, the third one, yeah. Right, which one, Louise maybe again, here you can tell me, is this the node or the antinode? The one that's moving the most?
It's anti-node.
Very good, it's antinode, yeah. And then this one here is node. Okay. Now they also want, what did I ask for? The second harmonic. So the second harmonic, that would be if there were 3 wavelengths inside. Isn't that what we said earlier?
Not 4?
Maybe 4. Let me go back to my picture I drew. There, second harmonic is 3 wavelengths. So it would look like this. Yeah. So, by the way, guys, can you imagine, please? I'll do this picture on the side, the one I'm just doing. So here's my pipe. And then here's my sound wave. 1, 2, 3. Now I want you to imagine there's a little bit of dirt or water or whatever on the bottom here. When the sound hits the water will move. So which parts of the water will move the most? Where do you think there will be the most movement of the water? Now if it helps, I can draw the other part in, so then it goes like this as well. So here, is this node or antinode? Node, and then here, anti, and then here, node, and so on. So what about here at the antinode? Will the water move a lot or a little? What do you think? Much movement or little movement of the water here?
I think it's moving.
It'll move because you have this sound wave hitting it. What about here? Move or not move? Not move, because the wave isn't moving. So in fact, what would happen, it doesn't have to be water, it could be like dirt, or, sand. So what you would get is, after a few minutes, you would get no sand here at the antinode, but the sand at the node doesn't move. So you get these little piles of sand here where there's nodes, and then the no sand at the antinode, because when the sound wave hits it, it makes the sand jump, and it will jump to where the node is, and then once it hits where the node is, it doesn't move anymore because the sound is not hitting it. Yeah. So I don't know, they sometimes ask you in the exam to draw this. They say like, there is some dust or some dirt in the pipe. Draw where the dirt will be and where it will not be if the sound is continued in the pipe. Okay? So the point is, where will the sound finish? At the node or the antinode? Where will the sound be at the end? The node or the antinode? At the node. Because all the sand at the antinode got pushed away. Yeah? Make sense? Yep. Yeah?
In the antinode, the
Yeah.
sound is...
Yeah? Huh? What are you asking me?
Sorry, can say
Say again, yeah. I'm saying the sand, you know what I mean by sand, don't you? You can ask Abraham what sand is. Yeah? He has a lot of it back home. You know sand, don't you? Like on the beach, yeah. So I'm saying where there's the antinode, there's no sand because the sound is hitting the pipe. Like this. So imagine if I have sounds here. So if I keep hitting this the sound will get pushed away. But here, at the node, the wave isn't moving, so then the sound just stays there.
Okay.
Yeah. So we're saying that the sound will finish at the node, and there'll be no sound left at the antinode. That's what I'm saying. You seem confused. Do you want me to write that down?
Yeah.
Yeah, okay.
Thank you.
No problem.
Actually, I don't understand the reason I need to more time to.
Yeah, that's fine. So we're saying that the sound will finish at the node. All the sound at the anti-node is pushed away. That's what I'm saying. Okay, there's one part left. Did you calculate the frequency? Yeah?
Yes.
So what did you get? Well, hang on, Louise, what did you get?
The frequency is
Yeah.
100.
100? Who, what did you get?
94.4.
Did you use a calculator? Okay, let's check it. Sorry, Louise, do you have this?
I get 100.
Oh no, do you have this written down?
Not yet.
No. That's okay, I'll do the calculation here. So, what did I have?
Oh, it's 100.
Hugo, what did you get?
I got 1,200.
1,200 for the frequency?
Yeah, because my wavelength is different.
Do you think you're right or wrong?
Because it wasn't, in my head, the wavelengths would be forwards on its distance. It would give me distance of the theory.
In the harmonic case,
Yeah.
we better read the question carefully. Sorry, which number? Let me have a look here. Sorry, I wasn't being clear in part 4 if I was talking about the first sound wave or the second one I drew. I really meant the first one. Did you use the second one? Yeah, sorry about that. And if you use the first one, you get 100? 100?
Yeah, I got 100 as well.
Okay, good. So we don't need to do that one. So that one's fine then. So we have 100 for that. Okay. All right. Now, if those speakers work, this would be really, really great. Like, it'd be great if these work because I can show you something fantastically cool. How can I see if the speakers work? I need to play a video, don't I? Volume. Okay, maybe this has no sound. Maybe I'll try a different one. Yeah. Yeah, it's that's plugged in. Oh, but is it plugged in here? It's not plugged in, it fell out, that's why it's not working. I think I will be okay. I think it's okay, thank you. Right. Oh, that sounded okay. Let's see now.
This is your all electric band with our Salmonic Brass Band.
Right. Now, I don't know if this will work because it depends on the distance, but I can try it. Let me see. I need a fundamental frequency note. No, I want the, you know what I mean, the same sound played over. Right, now, I don't know if this will work, but I can try it. If it works, I'll let you do it. Oh, this kind of does work. Yeah. Yeah. So what I'm making now is a sound wave between the two speakers. So there's a sound wave, but it's a standard sound wave. So at the anti-node, it's going very fast, so it sounds loud. And then at the node, it sounds quiet. So do this first. So down here, is it too loud? No, it'll be okay. Down here. Now don't move. Now walk slowly to the other speaker. You can tell. Now you stand where I'm standing and don't move. So where I'm standing here. Now Louise, you come up. So you stand by that speaker there. So the reason you're standing there is I want you to tell me if you hear it getting louder or quieter. So don't move. Stand perfectly still. And then Louise, you walk slowly to that speaker and listen if it's getting louder or quieter, okay? What do you think? Did it get louder or quieter? Yeah. So I want you to go back and then tell me where you feel it's the loudest. The loudest. Yeah.
The first step, the rest of them are still
Yeah, okay, yeah.
and second is another.
Okay. Now, I think this one is what? Is the volume changing? Or
I think so she's standing there, it's changing a little bit. Like right now, there's less, but usually it just keeps staying the same.
yeah, so Ugo's not moving, so it stays the same for him. But as you're moving across the room, you reach node, anti-node, node, anti-node. And it's the same with you down the back. When you move your head, you're moving between a node and an anti-node. Do you want to come up and try? You can sit down now, you guys. You want to, so if you walk, you can hear it. Yeah? All right, we'll stop you, John, man. So this is a standing wave, but for sound. So the video at the start was a standing wave for the rope, the string. But you can get it for sound as well. Okay? So let's have a look at the type of problem you could have with this. So we'll just do the example with the two speakers. So there's a speaker here, and there's a speaker here, and the frequency of the sound wave the frequency is 200. So I'm telling you that you know, when you started walking, there was a point when it's loud and then it gets quiet, but then it gets loud again. Yeah, because you're at the antinode, and the distance here is 0.85 meters. So my question is, what is the B? So I'll let you try this for a minute. I'll let you have a think about it. Now this is why you have to think very carefully about what the wavelength is. So actually, it's kind of funny because I'm picturing it now. You two down the back, you were moving your head and you could hear it getting loud and quiet. But if you think about it, this is just like Young's two-slit experiment. Because you have the sound wave coming out here, and then the sound wave coming out here, so it comes out, and then the two of them at the back, that's like the wall. So the middle, n equals 0, that would be like here, right in the middle, that's n equals 0. So this is where you hear the sound, and then when you move to the right it gets quiet, and then when you move more it gets loud again, and that's where n equals 1. Then you move to the right it gets quiet, then you move to the right again it gets loud, that's where n equals 2. Yeah? And if you don't move, it stays the same volume. But if you do move, you can hear the change in the volume. Okay, do you have an answer here for B? What did you get? Who? What did you get, Louise? No, it's okay, what did you get?
15.8.
Okay, something went wrong, I think. Abraham? Yeah? And Hugo?
Well, 85.
Yeah. So this is where I said you have to be careful. What is the wavelength here? It's not 0.85. That's not the wavelength. Yeah, why 2? Yeah. Yeah, if you draw it, it's like this. Here's the wave. And this is going up and down. So, when I say the distance between the antinodes is 0.85, you realize that's only half of the wave. The full wave is twice that. So anyway, the lambda is 2 times 0.85, which is 1.7 meters. And what's the formula for velocity? It's f lambda. So it's 200 multiplied 1.7, which is 340 meters per second. Okay. Okay, so that's standing waves. Basically I did questions 1, 2 and 3. There's one, number 4 is just like number 3. And number 5 is something we'll come back to at semester 2 maybe when we're doing more revision. It's a little bit, not that it's difficult, it's just a bit long. So what I think is enough, if you just make sure you try number 4, not now, but later today or something, number 4 is enough. Who? You said you did 6 and 7 in the last one? Huh? Can you just give me the answer for 6 and 7, if you have it? Or Ugo, do you have it for the last one?
The last one, like part 3.
6. Yeah,
All of them.
please. And do you have it?
The first one.
Yeah.
What's
The first part of 6, please.
2.4 times 10 to the minus 6
2.4 10 to the minus 6?
meters.
Yeah. And then number 2?
31.16.
Of course, yes. And number 3?
Well, because there's 2 answers from the 2 seconds. So the first one's 31 points.
Yes.
6, whatever it is. And the second one's 51.76.
Oh, okay.
No, second one. No. This is only asking for one angle.
Then there's anything I can go with.
So when you change the second one, minus.
Yeah.
Well, then
And-
I 32.
No, I get the final answer is 19.
19. Fine. And then part 3?
3.
3.
They got 3.5 2.8, because.
Yeah. And then,
Yeah.
no, 2.8 must be 3, yeah. And then finally in 7, last one.
8.07 times 10 to minus 14 meters.
Wow, that's small. And then the next one? Huh?
I know, yeah, it's hard to find.
Alright, so maybe I need to do 7 at some time then, is it?
No, I have it, so make sure he got the.
Alright, forget it, it's okay. Number 7, you have a different answer, which means not today, but sometime maybe I should do number 7, okay. And then the one from today, number 4. I mean, you could please try number 5, but if you look at today's one, number 5 is quite long, you see? I mean, try it, but at least do number 4, okay. Right, let's do revision. So what I would like to do is 1 mechanics, 1 electricity, and 1 waves question from section B. Okay, and then we have physics tomorrow, so we can do some more then. So what I picked out is, what I'll do first, because we're doing waves, we'll do a wave question first. So if you look at your book, 2013 B5, so what page is that? 2013 B5. If you go to page, that's not it, that's 2014, sorry, 2013 B5, that is on, yes, page 23. If you can open up to page 23.